All right, people. So, um, we just talked about how different things dissolve in water, right? The solute, the solvents, the weak electrolytes, the strong electrolytes. Now comes to the quantitative aspect, the aspect that involves calculations. Now, the calculations are very similar to stoichiometry, except we have a new way of measuring things or a new way of writing things down, and we call that molarity. Now, what molarity is it's a way of telling us how much of a substance is dissolved in a liquid, right? We call that the molarity. And there's a formula you must know. Molarity is equal to the moles of your solute divided by the liters of your whole solution. This basically tells you how concentrated something is. And it's very, very useful in calculations. And it's honestly just an additional step to what we did in the previous section. All right, so let's take a look at this practice problem here. Now, the formula we're going to be using is the molarity is equal to moles over liters. All right, so let's take a look at this problem. A 500-gram sample of potassium phosphate. Now, I'm going to have to ask Siri for the molar mass of potassium phosphate because I did not get that before the video started. Maybe I should have started that a little bit earlier. All right. Anyways, let's take a look. So a 500-gram sample. So we got a 500-gram sample of potassium. So that's K, not P. Phosphate. So that is PO4. Am I right? No, I'm wrong. So K has a charge of +1, and phosphate has a charge of 3-. So it's K3PO4. All right. But 500 grams of potassium phosphate is dissolved in enough water to make a 1.5 liter solution. So we have 1.50 liters of water. That's what we know. Now, the problem is moles. We need moles. So let's turn these grams into moles. Well, if you want to go to moles, then 1 mole must go on top. So 1 mole of K3PO4. And underneath, we need the molar mass of K3PO4. Because remember, the units have to match. We got grams of K3PO4 right here. We must have grams of K3PO4 at the bottom. So let's check this out. I want to make sure I have the correct molar mass. 212.27. Yours might be a little bit off. I'm using Google's molar mass, okay? You calculate your own. All right, so right here, so grams divided by grams, that's going to cancel, and we're going to be left with moles of K3PO4. And then how many moles is that? 500 divided by 212.27. And we end up getting 2.35 or 2.36 if you want to round up moles of K3PO4. Now we have the moles of solute. We have the liters of solution. So we know that big M is equal to 2.36 moles divided by 1.50 liters. And that's going to give us 2.36 divided by 1.50. It gives us 1.57 molar, you say 1.57 molar solution of K3PO4. Is that correct? That seems all right. So that's how you would write your answer. You would box it. And this right here, well, now if you had a different solution, and you wanted to mix them. Well, now you have a reaction that involves molarity with two. So things can get a little bit more complicated, as you can imagine, because this is only one reactant. This is only one species in the whole reaction. So once we start doing stoichiometry with all of them, you're going to need this step plus what we did in the previous chapter. Chemistry builds on itself, okay? So don't forget that. All right. Now, all right. Now, this is important right here. This is important because even though our concentration is 1.57 molar, the real concentration can be less than this because of what we learned about in the last video. Remember the last video I said that weak electrolytes don't fully dissolve? Well, that might be an issue when we have 500 grams and not all of them dissolve. So how do we account for that? That comes in chapter 11, I believe. It comes later in the book where we talk about partial dissociation of things. And once we get a little bit better at chemistry, we're going to go and revisit this issue. Okay, but right now we're building those fundamentals. We'll talk about the harder stuff a little bit later. But keep that in mind. Just keep that in mind. Things don't fully dissolve. Not all things fully dissolve. All right, so how do we calculate the concentration of ions? Remember I said, well, whenever you see an ionic compound and it's in solution, it breaks apart. So for example, CaCl2, well, it has one Ca and it has two Cls. So if you have 1 mole of CaCl2, well, you're going to have twice as much chlorine particles because 2 of them to make 1. So we're going to see that right here. So let's check this out. Look, 1 calcium chloride is made out of 1 calcium cation and 2 chloride anions, right? So for every one of these, there's 2 of those. So the concentration of Cl is going to be twice as much. All right, and then the calcium one is going to be equal to it. So that's something to keep in mind. Something to definitely keep in mind. And I think your book has an illustration on this. It does not. And if it, let's check it out. Illustration on this. Illustration. I think it's higher up. Sorry if I'm getting you dizzy. I apologize in advance. No, I thought I saw something. Oh well. Bad. Okay, I thought I saw something. Anyways, where was I? Let's do a little bit more examples. All right, let's take a look at this problem here. Calculate the concentration of chlorine ions if 0.70 moles of ZnCl2 are dissolved in 1.75 liters of solution. So we have 0.70 moles of zinc chloride. Now we are looking for chloride ions. So we know that 1 mole of ZnCl2 contains 2 moles of Cl minus because it takes 2 Cls to have a neutral compound. So that gives us 1.40 moles of chloride ions. And now we know the volume. We know the volume of solution, so we can calculate the concentration of chlorine in solution. All right. So we got 1.40 moles of Cl minus divided by 1.75 liters. And this is going to be big M of Cl minus. That looks hideous. But let's see, 1.4 divided by 1.75, 0.80 molar solution. Now, how many sig figs? We see how this one only had 2. That limits our precision, right? We can't go to 3 sig figs because this one only has 2. So always keep that in mind, that the data that they give you determines your sig figs, okay? All right. Now, let's do a little quick check. Which one of these has the greatest number of ions? Or of the greatest number of particles, right? So if we take a look at this and this breaks apart, that breaks apart into 2 things, Na and Cl. This breaks apart into Ca and then 2Cl. So this one has 3 particles. This one breaks apart into Fe and 3 Cls. So this one has 3 particles. But you got to take a look at the volumes as well, right? So basically what this is showing is number of moles. You have to be able to look at number of moles to help you determine what you're looking at, okay? So whenever you multiply big M times volume or times liters, you're going to get moles. And moles tell you how many particles you have, all right? Oh, I forgot. I didn't even check that one. But, yeah. No. Notice, the solution with the greatest number of ions is not necessarily the one in which... Okay, yes, that's very, very good. What determines how many particles are in there is not the volume. You can have a lot more particles in a very small container than you do in a very, very large container. For example, a concentrated acid. If you see a supersaturated or a concentrated acid, as concentrated as you can get, like let's say HCl at 12 molar, HCl at 12 molar has a bunch of particles. And even if you have a tiny little vial of it, very, very, very dangerous, as opposed to having like 10,000 liters of a small amount of HCl dissolved in it, right? If you have a small amount of it dissolved in a large amount of water, you still have a small amount of particles. So don't get distracted by the liters, all right? In that previous example, there was 800 milliliters of sugar, of your sucrose, but sucrose is only 1 particle. So this one actually, I believe, had the least amount. I didn't do this in my head. I didn't want to waste your time. And I think you can do that on your own. All right. And then the formula unit has the greatest number of ions. That's also incorrect. You saw how this one, it had the most ions, but it had a lower volume. So it's actually a combination of both that determine it. That's why it's big M is moles over liters. It's dependent on 2 things. It's dependent on the quantity, and it dependent on the, well, actually the moles is really what determines your particles, not your liters, just your moles. All right, but your liters are gonna help you determine your moles. All right. Now a little bit of nomenclature and little things. Sorry, this is kind of a long video. I thought I was, all right. Almost done. Now, there's a little bit of things you need to remember, or you need to memorize. A standard solution. A standard solution is a solution that has a very, very accurate concentration. Usually something like this you will buy from a manufacturer, and or you do experiments to verify its accuracy. We're going to do some experiments where we have to make a standard, and we're going to test our standard, and we're going to measure how the exact concentration, because sometimes the manufacturer will send you a 1.0 molar HCl, but whenever you run a test, if you run it like 50 times, it's always going to be off by a little. Well, if you standardize your HCl and determine the actual concentration, you might find that it's actually 0.98 molar, or you might find that 0.90 molar. So the label isn't always accurate. Things evaporate, things evaporate, so the concentration can go up. There could be contamination or just slip ups. A stock solution. A stock solution is what you get materials from to dilute. So if you had like a 2.0 molar solution, but you wanted a 1.0, a 0.5, a 0.25, what you would do is you would get this one diluted by half, diluted by a fourth, diluted by an eighth. All right. So that's what the purpose of a stock solution is. We're going to do an experiment or just lab practice with these two. And the dilution is the process of watering down substances. Now, the dilution affects the concentration. It affects the number of particles per liquid by changing the amount of liquid. It doesn't change the amount of particles. It just changes the amount of solution. It changes the amount of water that is there, so the particles are more spread apart. All right. Now, the dilution equation is M1V1 equals M2V2. And I should check if I need to take a little pause here, or if we're going to just do it all. Where was I? You know what? I think we'll call it quits right here, and we'll talk about the dilutions later on, okay? Actually, nah, we got this. This is 4. Yeah, you got 4 more minutes. You can do this. Now, let me see. So let's take a look at this formula really quick. Mr. Sanchez, why aren't you prepared? Shut up. So this equation is very, very simple. All right. This equation is very, very simple. The M1 and the V1 are your initial concentration and your initial volume. And then your M2 is your second concentration and your final volume. So whenever you multiply molarity times volume, you get moles. So let's say I have 1 mole of sugar, or 1 mole of NaCl, and I dissolve it in 1 liter. I'll have 1 molar. I'll still have 1 mole of particles dissolved in there. But if I have 1 mole of NaCl and I dissolve it in, like, let's say 300,000 liters, well, now I have a bunch of water, but I have the same number of moles. So what it's saying is that the number of moles don't change if you change the liquid, or how much water you add, which is kind of no duh, right? Because things stay the same. You just add more water. You didn't add more of your chemical, you just added more water. So let's explain this. So what volume of 16 molar sulfuric acid must be used to prepare 1.5 liters of a 0.10 molar? Little tip when reading problems, the word of a is a unifying word. It means it puts data together. So 1.5 liters and that 0.1 molar, that means they go together. So they're most likely going to be these two. All right. So what volume of 16 molar sulfuric acid must be needed? So we figure out that, but we know the molarity. So let's put 16 molar sulfuric acid, and we don't know our starting volume. We don't know how much of it we need. We don't know how much of it we need, but we know we want to make 0.10 molar, and we want to make 1.5 liters of it. So let's do a little bit of math. So let's divide that 16 molar to both sides, and then V1 is going to be equal to everything on the right. So let's do this. It's 0.1 times 1.5 divided by 16. that gives us 0.0004 liters. So we need that many liters to make our solution. So I know I'm done with the sample problem, but I want to explain like what it really means. All right. So how would you do it? So you basically have a bottle or a container of some very spooky stuff. You have 16 molar sulfuric acid, dangerous stuff, super scary. Now, what you're going to do is you're basically going to get 9.4 milliliters. You're going to get 9.4 milliliters. That's a very, very small amount. And you're going to add it to 1.5 liters of water. Or you're going to have a container. You're going to put your 9.4 milliliters of your acid, and then you're going to add about 1.4 1.41 liters of water. So you're going to add a bunch of water until it reaches 1.5, and then your substance is going to be diluted. It's going to be the concentration you want, ready to do your experiment. Okay. These problems aren't bad. I just think you guys are going to have a hard time doing this in experiments. A lot of times you know how to do the problem, but you have to be able to translate that to the lab skill. This is a lab skill that you must have. You should be able to dilute something. You shouldn't have to come to me, Mr. Sanchez, we only have 1.0 molar HCl, but the lab report says we need 0.5 or 0.7. Well, you should figure that out. You're doing this, okay? But anyways, that's about it. That wraps up these types of problems. I don't think you need to do this, but peace out, people.